Changes in motion are produced by a force or combination of forces. A force, in the simplest sense, is a push or a pull. Its source may be gravitational, electrical, magnetic, or simply muscular effort. Here's a box of candy, say in free space. It's free to move. Let's suppose we exert a 5-Newton force on it. That's a bit more than 1 pound. This red arrow drawn to scale is a vector. A vector is a pictorial arrow that shows both magnitude, how much, and direction, which way. The 5-Newton force can produce a pickup in speed of the box. Suppose we exert a second identical force on the box. The pair of 5-Newton forces will double the gain in speed. But you know what? The behavior of the box would be the same whether acted on by the 5-Newton forces, both of them, or a single 10-Newton force. The box wouldn't know the difference. We say the net force of the two 5-Newton forces is 10 newtons in the same direction. The forces simply add. Suppose we pull on the box with two oppositely directed forces, one 10 newtons to the right and the other 5 newtons to the left. How does the box move? Here forces subtract, and it moves just as if a single 5-Newton force acts on it. The net force on the box is 5 newtons to the right. Suppose a pair of 5-Newton forces in opposite directions act on the box. What then? They cancel out. The net force on the box is 0. When the net force on something is 0, no change in motion occurs. We say the box is in mechanical equilibrium. Consider little gymnast Nellie Newton, who weighs 300 newtons, which we represent with a red vector, downward in the direction of gravity. 300 newtons is about 66 pounds. She holds onto a bar that's supported by a rope attached to the ceiling. We neglect the weight of the bar. The rope is taut under a stretching force called tension. Since she's at rest, the rope tension has got to be 300 newtons upward. So 300 newtons upward and 300 newtons downward produce a net force of how much? I hope you said 0. Nellie is in mechanical equilibrium. Suppose 3 ropes support Nellie, and evenly, so the tension in each rope is the same. We know the sum of the tensions have to add up to 300 newtons. So what's the tension in each rope? Did you say 100 newtons? If so, good. Again, Nellie is in equilibrium. Let's go for 2 ropes. Again, evenly supporting Nellie. What's the tension in each rope? Can you see it's 150 newtons? Suppose instead of attaching the left rope to the ceiling, we fix the end to a wall with this pulley arrangement. The pulley simply changes the direction of the rope, not its tension. So how about tension in the right rope? It will still be 150 newtons. How about tension on the left rope? It turns out it's still 150 newtons. Interesting stuff may occur beyond the pulley, which doesn't affect Nellie. Nellie is in a system bounded by the white dotted box. What occurs outside the system is immaterial. The forces inside Nellie's systems are the ones that count, and they cancel to 0. We don't show the ceiling in these cases. Most ceilings are horizontal. But suppose the ceiling is slanted, so the vertical ropes have different lengths. The rope on the right is shorter, even shorter than the length of the vector we draw to show its tension. Will rope tension and its vector there be affected? And the rope on the left is longer? Maybe a longer vector there, or not? Some beginning students think that the length of a vector relates to the length of the rope. If that's you or your friends, you'll soon learn to progress beyond that. I want to leave you with a question. Assuming all conditions for Nellie are the same, except for the slope ceiling, will the vectors representing rope tensions still each be 150 newtons? And can you defend your answer? I hope so. Until next time, good energy.